Hi, this is Anthony Garland, and I'll be going over my presentation, Multi-Objective Optimal Design of Functionally Gradient Materials. And it fits within to the Design for Additive Manufacturing field. And Dr. George Fadel is my PhD advisor at Clemson. So this is the outline of what we're going to cover. First, motivation about the topic of functionally gradient materials. Then talk about what are gradient materials, what is topology optimization, what exactly we're trying to do with fully optimal functionally gradient materials, and look a little bit at literature, and then look at the proposed method, results, and conclusion. So first, the motivation. Motivation is additive manufacturing, and what exactly is that? If you're not familiar with it, additive manufacturing is the process of joining materials layer by layer from digital data directly from a computer. And this is in contrast to like machining and removing material away from like a solid block. It's had exponential growth since its start. This is a very hot topic right now. So what are the gaps that are holding back additive manufacturing? There's really four main areas. First is the materials development and evaluation. That is like when we go to make something with additive manufacturing, what are the materials that we're going to use for that, and how can we characterize them? For example, a lot of the sintering processes are very sensitive to like the humidity and other things like this, and also like the particle size. The next gap is the design methods and standards. Since additive manufacturing is a totally different manufacturing process, our way of approaching the design should be different to take into account the unique capabilities and limitations of additive manufacturing. The third is the modeling and monitoring of the actual process itself, so that we can make sure that the manufacturing process is doing what we want it to. And finally, once we make something, we need to characterize its material properties and its overall structural properties to make sure that it's going to behave like we expect when we put it into an actual object. And finally, this top box, it's showing that all these need to work together in order to make a full workflow and a full certification or design and certification process. So this research fits into this design methodologies and standards. So within additive manufacturing, we can design multi-material or gradient materials. This is a big advantage, which you can't do with traditional manufacturing. We can also do really complex geometries, and also we can automate some of the design process and this is going to be required if we want mass customization of products that are customized for individual users. So when we bring those three together, we're really interested in automated design tools which generate optimal topologies and also generate optimal material gradients at the same time. So what exactly are functionally gradient materials? A functionally gradient material is when you have two or more materials within a single object, and this is similar to composites, but it's very different as well. So we want to take advantage of diverse properties from different types of materials, but instead of having just a single layer of one material and then a single layer of the next, we want to have a smooth transition. So in this picture, we have a transition from steel to copper coated nickel, and this picture on the left is actually the cross-sectional view of the part that was actually fabricated with additive manufacturing. So the question is like, how do we design this gradient within the part? And the reason why this is interesting is because we can actually fabricate these with additive manufacturing, whereas other manufacturing processes, it would be very difficult or impossible to make these gradient materials. So here's two pictures. This one on the left is a direct metal deposition process, where there's metal powder being shot into a laser, which is melting the particles in flight, and then they solidify onto the substrate, similar to welding. But by changing the material that's coming out of these nozzles, you can make a gradient material. Similarly, for this, this is just a graphic of a FDM 3D printer, which is the common cheap consumer type 3D printer where you have like two-stepper motors that are pushing two different filaments into a single melt chamber, and by controlling how much of each material is being pushed into the melt chamber, what comes out will be some type of mixture of the two. So by changing the ratio of the two, you can make a gradient material. So why do we care? We care because it allows us to customize the regions of a single part. So instead of having to put together like an assembly that has multiple different materials, we can fabricate a single part that has diverse properties throughout the single part. So in this example, you have a high temperature pressure vessel, and we really have two big ideas, or two main objectives. First, we don't want the thing to melt. Seems pretty obvious. The second one, build it withstand high pressure. The problem is that ceramics, which are good at resisting heat and not melting, aren't necessarily as strong as certain types of metals, at least in certain ways. So by making a metal a ceramic and then transitioning to a metal on the outside, you get the high heat resistance of the ceramic and the high strength of the metal combined together into a single part. So that's what function gradient materials are. Now, what is topology optimization? Maybe you're already familiar with it. If you're not, this is just a quick overview. Topology optimization is concerned with trying to find the optimal placement of material within a domain. So there's several different types of methods that you can use. One is called homogenization. There's also it's called the SEMP method, level SEMP method, and also some evolutionary techniques. So we have a domain, and we'll find, for example, the optimal truss. The topology optimization will slowly change the design in order to get the optimal placement. So really the goal of this research is to be able to combine the topology optimization and gradient material optimization. So what exactly does that mean? We want to find the material void boundary, like where there is material and where there is not material. And also within the material regions, we want to know what the best combination of the two materials is. And we expect that the results will be complex designs because we're specifying not only the shape, like for example, if you're designing something in a standard CAD, you are defining the shape, but also we're defining the material distribution, which most CAD applications cannot do, like you choose a single material. So some researchers that have done some work with this, Xia and Wang, they provide like a really nice paper that gives a clear description of how their algorithm works. Their algorithm is not the most stable. It's also limited to a single material model. Dunning et al., they give a very high level view of some of the challenges with combining the two. However, they leave out a lot of detail. It's kind of hard to follow their paper. And in Jabali et al., they give this really interesting and unique evolutionary approach, but it doesn't really extend to multiple materials. And also, they admit in the paper, and also you can show that it's not necessarily the optimal placement of the two materials. But they try to reduce the number of design variables by basically combining topology and the gradient material. So in this research, we're going to extend Xia and Wang's gradient and topology technique together and try to make it more stable. So we're going to do a similar two-step method where we run several steps of topology optimization and then several steps of material gradient optimization and go back and forth between the two. I'm going to say one more thing. So one of the key differences is that the gradient material optimizer will use a target ratio of the two materials instead of a maximum amount of one material, which is one of the reasons why the Xia and Wang's original algorithm was not stable. It's because both the topology and the gradient were they were passing variables back and forth and made it difficult for it to become stable. So in our work, we're going to say the topology optimization is just targeting a total volume of material as its constraint, whereas the gradient optimizer doesn't really care about how much total material there is. Its constraint on the optimizer is the target ratio of the two materials. So we're gonna, in addition to that, something else that we want to do is a proposed benefit of gradient materials is that they can customize regions. However, I haven't really seen a whole lot of that in the literature. So in this example, we're going to combine two different types of simulations. We're going to do an elastic analysis and also a steady state heat transfer analysis of our domain and try to optimize for both of them. Because this is really the main advantage of gradient materials, is being able to have a single part that can achieve diverse objectives or that are conflicting objectives. At least the design itself will be conflicting. So we want to consider two objectives, and one of the tricks is that when you calculate the sensitivities for the topology and material gradient optimizers, is that they're going to be in different units. So we're going to normalize them by dividing by the greatest value, and then we'll combine them together from the topological sensitivity for the elastic objective and also the topological sensitivity for the heat objective. And then because there's two objectives, we could just do a weighted average, a weighted sum of my two objectives, and we'll use that in the sensitivity analysis. So it'll go something kind of like this. We have an elastic FEA, also a steady state heat transfer FEA. We calculate the topological sensitivity for both and also the material change sensitivity, and then combine them together for both types of optimization. And this combining is where we have to do the normalization in order to make the units, make it unitless so that they can actually be combined in a meaningful way. Then the next key idea is that on the topological optimizer, the constraint is a total volume constraint, whereas on the material gradient optimizer, we're targeting a ratio of the two materials. This allows us then to update the topology and also update the material gradient in a way that makes the algorithm more stable. Alright, so for an example, so I tried to use the same material properties as the Xia and Wang paper to make it more clear how it compares. So we have two materials. The first one is stiff, so it's an elastic modulus of 1, and the heat transfer coefficient is low, 0.02. Whereas the second material is not as stiff, it's about 1/4 as stiff, and then the heat transfer is twice as high, so it conducts heat twice as good. On the left side of this domain, we have a fixed area, so this is like attached to a wall, and then there's a load off to the right. Then I'm applying a heat load everywhere in the domain. And there's a heat sink in the middle. So our goals are to maximize the stiffness of the structure and to minimize the temperature at the same time. It turns out those are the optimal designs for each one of those with these boundary conditions will be conflicting. So we want to see what the designs will look like with the conflicting design objectives. Like I said earlier, we're also doing a weighted objective. So I'm going to show some examples where we're actually going to show all the examples where I'm going to change the weight on the objective from 0 to 1 in increments of 0.1. So if I consider the weight on the elastic objective to be 0, then that means I'm only considering the heat transfer objective. And the result is a good design like this. Now, the blue material is the material that conducts heat better, but it's not very stiff, whereas the green material is the stiff but poor heat conductor. So with the design, you see clearly that the heat sink in the middle is all blue, and then you have these like fingers kind of coming out from the domain, kind of like what we'd expect with a heat sink. And then the green material is on the outside of each of these fingers. Down here at the bottom, I'm tracking my two objectives and also my constraints. So the yellow might be a little bit hard to see. That's the volume fraction of material 1. The purple is the volume fraction of material 2. Then my heat objective is in the red, and my elastic objective is in this green color. So you can see that the heat objective drops off rapidly, and after about 50 iterations, it's about where it's going to stay for the rest of the time. You can see after about 150 iterations that the the volume 1 and volume 2 have stabilized. In this example, because we're not really concerned about the elastic objective at all, it's just going all over the place, and which is what we'd expect since we're not even considering. Now as I change my objective to consider just a little bit of the elastic objective, you see our design is much different, and that it looks kind of like a truss, but it has these really interesting finger-like features sticking out. Remember, the load is right here on the right, and then the left side of the domain is fixed. Then as I increase the weight on the elastic objective, my design changes a lot. So this is the 50-50 between the elastic and heat transfer objectives. You can see that both have dropped off significantly. This blue or green and the red objectives have decreased from their initial value significantly. Also, just the general design is really fascinating because the green is in the kind of like along these bars, whereas the blue is in the middle where the heatsink is, and you have these like fins that are sticking out from the truss that are made entirely of the blue material, which is what makes sense because it's not contributing to the elastic objective at all. It's only contributing to the heat transfer objective, so there's no reason for it to have any green within these fin-like features. Then as I get closer and closer to only the elastic objective, my design changes so that the green is 100% in the middle, which is what you'd expect, and then the blue is on the outside. So here's a video of it optimizing. This is the 50-50 case, where I'm considering 50% of the elastic objective and 50% of the heat transfer objective. The topology optimization, in this case I'm using the SIMP method. However, if you wanted, you could substitute in a level set or whatever else you, whatever your favorite topology optimization technique is, and it should pretty much work the same way. So again, it's really fascinating that you get these like fin-like features that are sticking out from the main truss, and the fins are made entirely of the better heat conducting material, whereas the bars of the truss are made entirely of the strong, stiff material. Okay, so we can do a Pareto frontier plot of the two objectives, and then so that's what this top one is, and obviously the 0 point, when I'm considering just the heat objective or just the elastic objective, that the other objective is going to be really poorly achieved. So the designs between point 2 and point 9 form a nice curve here on the second graph, where I've just zoomed in to where most of the points are clustered. So ultimately the question is, does this gradient material design actually perform better than a single material design? Because that's really what we're interested in. Because can we achieve high performance parts with the gradient material? So in this case, I did a comparison of comparing single material designs to the gradient material design. So on the far left, this design, I'm using 100% of the material 1, and I'm not using any of material 2. So material 1 was the better, it was the stiffer material that doesn't conduct heat well. And you can see that the elastic objective, which is the purple one, it's the lowest of all of them. So in this case, because this is a minimization problem, I'm trying to minimize the strain energy and minimize the temperature, the minimum on the purple and blue bar, that's the better design. So the minimum is achieved of all the designs by using just the stiff material, which makes sense. Then if I consider just the better heat conducting material, just the blue material, you can see that my elastic objective is the worst, which is what you would expect, but my heat objective is much better. then again I'm using 40% of material in the domain, and 40% is going to be just the volume or material too. Then if I consider 20% of each material and apply the same analysis, then, but it's not a gradient material, so it's a homogeneous material that has properties that are halfway between material 1 and material 2. If I run the analysis, if I run the optimization, and I look at the objective values at the end, then I get these values. So you see my elastic objective is it's higher than just a single material design, but it's much better than the material 2 design. My heat transfer objective is still pretty high, but it's lower than the first design. Finally, in the last column, we have a gradient material design. So in this case, I'm using 20% of each material, but instead of being homogeneous, I'm allowing the material to change within the design. And here's the picture off to the far right. My elastic objective, see, is lower than its corresponding homogeneous material design. And then also the heat objective is a good bit lower than the homogeneous material design. So by using the same amount of both materials, I'm able to better achieve my objectives by designing a gradient material part, which is really exciting because that was the proposed benefit of the gradient materials from the very beginning, that we could better achieve multiple objectives. It turns out there's a 20% improvement from design 3 to design 4, and that's huge. That's a lot. So in conclusion, we were able to generate functionally gradient material designs which consider 2 objectives and have an optimal topology. And the ultimate goal of this is to make multifunctional parts. In this analysis, we might not be getting the global minimum, but our designs are certainly closer, or they're certainly better than the homogeneous material design, but I haven't done a rigorous mathematical analysis to prove they're the actual global minimum. I used the SIMP method, which certainly has its pros and cons. You could use another method of topology optimization if you wanted. This work has a lot of limitations. For example, how we combine the simulations. Might want to use a multidisciplinary optimization technique instead of the way I did it. And in my designs, there was still a sharp transition between the 2 materials. So if considered like thermal expansion and the stresses that would cause, then perhaps the gradient material design would not be as good. It's one of the proposed advantages of gradient materials is that it's able to minimize these sharp transitions between materials that you might experience in a composite, but I didn't take that into account. Finally, I used a linear material interpolation. Since then, I've also improved the algorithm a lot. I've also tried some other material interpolations. I've changed the number of steps between the material gradient and the topology optimizer. Also, I've added like a termination criteria instead of just running for a certain number of steps like that. So we've worked on some of these limitations since we wrote the paper for this presentation. There's still a lot of work that we could do. Okay, and if you have any questions, feel free to email me. Thanks for watching.